In this unit, we talked about geometry. In 4.1, our objective was to be able to calculate the volume and surface area of three-dimensional shapes, identify their cross-section, and calculate 2D properties of that cross-section. Our question is, what's the relationship between pyramids and prisms, as well as with cones and cylinders? So 2D and 3D stand for 2 dimensions or 3 dimensions. The 2 dimensions are length and width. However, in 3D, we have an added piece of height. Some properties of 2-dimensional shapes include both perimeter, or the length around an object, and area, the number of square units that cover a closed figure, the inside piece. In 3 dimensions, we can calculate both volume and surface area. So words that would indicate volume are going to say, how much will something hold or take up? Whereas surface area is going to ask you to solve for the areas of all the sides that you can see. So on the left-hand side, we have our normal Cartesian coordinates in 2 dimensions. However, on the right-hand side, we have Cartesian coordinates that are in 3 dimensions, our x-axis, our y-axis, and our added z-axis. In 2 dimensions, we have shapes like squares, circles, triangles, and rectangles. However, in 3 dimensions, we have cones, cubes, prisms, spheres, and cylinders. I think of it kind of like animations. On the left, we have Beauty and the Beast's Belle. That's in 2 dimensions. However, Frozen is in 3 dimensions. So we're going to start talking about prisms. There are a bunch of different types. However, there are only 3 pictured here. The volume equation is base area times height. Now, base area is exactly what it sounds like, the area of the base, which depends on the shape of the base. So if my base shape is a rectangle or a square, the way to calculate my base area would just be L times W. But if my base shape is a trapezoid or a triangle, that's going to change how I calculate that base area. Surface area comes from taking both bases and multiplying them. So we've got 2 bases and we're going to multiply their areas. And then we need to take all of the areas of the exposed sides. So in the case of a triangular prism, there are 3 sides that we would need to calculate the area of. For a rectangle or a cube, there are 4 additional sides that we would need to calculate the area of. And the best way to do it is to take the perimeter of the base and multiply it by that height factor. If I were to cut any of these shapes perpendicularly, in other words, up and down, for an object that sat on the ground, for a triangular prism, I would see a rectangle. For a rectangular prism, I would also see a rectangle. And for a cube, I would also see a rectangle, in this case, more specifically, a square. However, if I were to cut those shapes parallel, I would get a triangle for the triangular prism, a rectangle for the rectangular prism, and again, I would get a square for the cube. So I want you to take a moment and think about how I could take a 2-dimensional shape and use that to make a 3-dimensional shape. In other words, I can give you unlimited access to whatever shape you would like. What would you do in order to give it that 3rd dimension, that height that it's missing? So think about it like this, like the example on screen says to stack a bunch of cards on top of each other, because once you have a stack of cards that fit into that box of cards, that becomes a prism. All right, another example with a rectangle shape is to take a bunch of pieces of construction paper and put them on top of each other until you get a pack of construction paper. That's a rectangular prism. The example that one of my students said in class was if you stack a bunch of slices of pizza on top of one another, you get a triangular prism. The next shape we're going to talk about is a pyramid. You can have multiple different types of pyramids that depend on the base shape. In this case, we have a triangular prism and a rectangular prism. Again, it's still base area times height. However, we've got that 1/3 out in front, which means we're gonna take whatever that volume is and then divide it by 3. So again, base area does depend on the shape of our base. However, for our surface area, we don't have 2 bases like we did for prisms. We only have 1 base. And then we have, again, our perimeter. All right, but our perimeter this time, instead of making rectangles all the way around, we've got triangles. So we have that 1/2 factor in front because our area of a triangle is 1/2 base times height. So we're taking that into account. Now, when I talk about height for those triangles that are along the sides, I don't mean the direct height. I mean the length of the slant because that's the area that we want. We want the area of the slant. If I were to cut any pyramid up and down, I'm still going to get a triangle. However, if I cut it parallel, left and right, depending on my base shape, the shape of my cross section could change. I can make a pyramid by stacking smaller and smaller base shapes on top of each other. In other words, I can start with an extra large pizza box and then put a large pizza box on top, a medium on top of that, a small on top of that, and then an extra small on top of that. So overall, my general base shape is the same. It's just getting smaller and smaller and smaller until the very top, it's just a point. Our third shape is a cone. It's very similar to a pyramid. However, our base shape is a circle. So for our volume equation, we've got 1/3 base area times height again. However, my base is a circle and the base area of a circle is pi r squared. So we just added some substitution in there. Our surface area is going to be pi r squared, the base, plus pi r s, where again, s is that slant height. Sometimes, if it's not given, you have to use the Pythagorean theorem to find the slant height. If I were to cut a cone perpendicularly or up and down, I would get a triangle. And if I were to cut it left and right, you would see a circle. Similarly to a pyramid, if I wanted to create a cone from two-dimensional shapes, I could stack increasingly smaller circles on top of each other. So I could stack a quarter, on top of that a nickel, on top of that a penny, and on top of that a dime, and that would create the general idea of a cone-shaped object. However, another way that I could make a cone is to rotate a triangle around in a circle. So the example that I kind of performed in class was take, for example, those skirts that when you start spinning really quickly, they fan out and they make a cone shape. So that's the idea of taking a two-dimensional object and rotating it until it makes a three-dimensional object. And I realized that that's kind of complex because the skirt is already 3 dimensions. However, the general idea of the rotation is still the same. The fourth shape is a cylinder. A cylinder is similar to a prism. However, its bases are circles. So we're going to have, again, that our volume is base area times height, but our bases are circles, and the area of a circle is pi r squared. For surface area, we've got 2 of our bases, so we've got 2 pi r squareds, plus the perimeter of a circle, which we call the circumference, 2 pi r, times the height, h. If I cut it up and down, I get a rectangle, and if I cut it left and right or parallel, I see a circle. And I can make a cylinder in one of 2 ways. I can either stack circles on top of one another, or I can rotate a rectangle around and around and around. So sometimes those, I don't know what they're called, windmills, I guess you could call them, they're rectangular shaped, and in the wind, they start spinning really quickly, and you can kind of see the outline of a cylinder shape. Our last shape is a sphere. So the volume of a sphere is 4/3 pi r cubed, and the surface area is 4 pi r squared. No matter how I cut a sphere, I always get a circle, and the only way to get a sphere is to rotate a circle around an axis. So let's do a couple of examples. The first one. We are given that a soup can has a diameter of 10 and a height of 15. And we need to find the volume of the soup in the can. If there's a little bit of space at the top, that's just air. Okay, so the first question is, what shape is a soup can? If you said cylinder, you're correct. So we're given the diameter, but we don't really care about the diameter. That's not in any of our equations for cylinders. We care about the radius, and the radius is half of the diameter. We also know that the height is 15, but there's that little bit at the top for just space. So the height of the soup is 15 minus 0.5. So now we have our equation for volume, which is pi r squared h. We've got r and we've got h, so we simply plug it into our calculator, and volume is in cubic units. In this case, it's cubic centimeters. For the next example, we need to find the volume of a cone-shaped building with a height of 12 and a radius of 7. So we know that our volume of a cone is 1/3 pi r squared h. We know r and we know h, so we plug them in and we get another number in units, again being cubic centimeters. So remember what I had said about a couple slides ago. What happens when I rotate a circle? What shape do I get? A sphere. What happens when I rotate a triangle? Think of the ballerina's skirt. I make a cone. And lastly, if I rotate a rectangle, I get a cylinder. Let's talk about some cross sections for a little bit. We can have a bunch of different types of cross sections. It can be parallel, perpendicular, diagonal. We're only going to talk about parallel and perpendicular. However, it is important to note that others are possible. So looking at the one on the left, is that parallel or perpendicular to the base of the shape? It's parallel. What shape would it make? A rectangle. Now let's look at the middle example. Is that parallel or perpendicular? It is perpendicular, and it would indeed make a triangle. The last one is a little bit harder to visualize, but it is a parallel cross-section, and the shape that you would see is a rectangle. If you're having trouble, I'd highly suggest getting some Play-Doh or something that you can cut so that you can see what that shape looks like. All right, we've got a couple more examples to work through here. We are given a cylinder with a height of 60 and a radius of 20, and we need to find the area of the rectangle formed when we cut it up and down or perpendicular. So let's think about what each of those measurements are. Our height is 60, so our height of our rectangle is also going to be 60. Our radius is 20, but keep in mind what the definition of radius is. It's from the middle to the outside. So our length of our rectangle is actually going to be 40. And our area of a rectangle is length times width, so 40 times 60 gets me 2,400. And because it's area, it's square millimeters. In our last example, a rectangle has a length of 3 and a height of 5, and we're asked to find the volume of the cylinder made by rotating. So we're going to pretend that we're rotating it exactly like the image above, in an axis that's right down the middle, which means that that length of 3 is going to get cut in half because that length is going to become the diameter, and we don't care about the diameter, we want the radius. So our radius would be 1.5. Our height still stays as 5 meters. When I plug that into my volume equation, I get 35.34 cubic meters. If you were to spin it on its terminal axis, in other words, around one of the edges, that would change our volume. In 4.2, students will be able to describe the relationship between mass, volume, and density, and discuss how interactions between the object's mass and volume affect its density. So the equation for density is mass divided by volume, and by doing some simple manipulations, we're able to figure out how to isolate mass and isolate volume. So if I want to get mass by itself, given the density equation, I would need to eliminate that divided by volume. So I would need to multiply by volume on either side, thus getting me that mass equals density times volume. From that, if I wanted to solve for volume, I would need to get rid of the density times volume. So I would divide both sides by density, giving me that volume equals mass divided by density. Like we discussed earlier, volume is the measure of how much space an object takes up. Keywords that would signal you to calculate volume would be how much space does this take up? How much could you fill? How much makes up? Or how much could this shape hold? The volume of a solid is measured in cubic units, centimeters cubed, inches cubed, etc. Mass is the amount of matter that an object has. It is different than weight, which is the measure of the pull of gravity on an object. Your weight will change depending on where you are, Earth or the moon, but your mass will not. The unit of measurements is typically grams or kilograms, so you know you have a mass if you see a G or a kg. Density then is the measure of how much mass is contained within a certain space. It's mass per unit volume, and the unit measurement for density should represent both mass and volume. So for example, grams per centimeter cubed, kilograms per liter. So it'll always have that slash. So let's do these two examples. You have a graduated cylinder with 50 milliliters of water, and you put your 50 gram sample into the water and notice the new volume is 57. What is the density? Okay, so we've got 50 grams. That indicates that our mass is 50. Our volume is how much the water changed when we put it in there. So originally the water was at 50, and then with our stuff, the water went up to 57. So our stuff must have a volume of 7. Thus, I can divide density equals mass divided by volume. So density equals 50 divided by 7. So our density is 7.14 grams per milliliter. On the right-hand side, we have a 4x3 picnic blanket, and there are 45 ants. So this one is a population density question. It's similar because it follows a very similar equation. However, our numbers for mass are going to change just a little bit. Our mass here is the number of ants, and there are 45. Our volume, so to speak, isn't really a volume because a picnic blanket is a two-dimensional shape. Thus, our, quote, volume is now an area, and our picnic blanket 4x3 has an area of 12 meters squared. So to find the density of ants per square meter, we would need to divide 45 ants by the 12 meters squared and get 3.75 ants. But logically, that doesn't make sense. You can't have 3/4 of an ant. So we need to expand our space until we get a whole number. And we can't get a whole number until we expand the space by 4. So that becomes 15 ants for every 4 meters squared. In 4.3, we applied geometric concepts to solve design and optimization problems and talked about the significance of some of the solutions as well as the types of questions that could be asked involving this topic. For example, your friend has 2 chocolate bars and offers you either bar. You have to choose one. One is the shape of a triangular prism, and one is a square prism. All right, so I realize both of these are not chocolate, but hopefully the shape helps you to identify what it is we're talking about. We're talking about a Toblerone versus a Ghirardelli chocolate square. I went ahead and I labeled all of our numerical pieces. So our triangular prism has a base that's 3 centimeters wide, 2.5 centimeters high, and 3 centimeters long. Whereas our square has a square base of 3, which means its length and its width is 3, and its height or length in terms of depth is 1.2. To find out which one contains more chocolate, we need to find the volume of both. Because they're both prisms, they have the exact same volume equation. However, the numbers that we're plugging in change. Our base shape on the left is a triangle, and so we have to find the area of the triangle, which would be 1/2 3 times 2.5. We then need to multiply that by height, or how long the chocolate bar is, which is 3, thus giving us a volume of 11.25 cubic centimeters. On the right, our base area is a square, so we need to calculate length times width, or in other words, 3 times 3, multiply it by our height, which was 1.2, and get 10.8 cubic centimeters. So we should choose the Toblerone bar because the volume is larger. You want to buy a gift for your favorite math teacher, me, and there are 2 different wrapping options. The first option is to place the gift into a rectangular box, and the second is to place the gift into a cylindrical box. I've gone ahead and drawn the diagrams as well as labeled them. All right, and it asks you which one is going to cost the least to wrap. So I want you to tell me when I'm talking about wrapping paper, where do I put wrapping paper, / what kind of problem would this be asking me to solve? If you're thinking surface area, you are on the right track. So I've gone ahead and I've put the surface area equations on there for us. So we've got 2 times the base area plus the perimeter times the height. All right, now I realize that it's going to be a little disorienting to kind of see how I did the math. However, you can choose any of the sides to be your base. I chose the ends on the right and left, the smaller sides. I chose those to be my base. So my base area is going to be 30 times 40. My perimeter of that base is going to be 40 plus 40 plus 30 plus 30 all the way around. And then I left my height as 50, thus giving me a surface area of 9,400 inches squared because it's area. Now for the cylinder, I've got 2 pi r squared plus 2 pi r h, and those numbers are a little more obvious to plug in, and I get a surface area of 8,792. So already, without calculating how much money I'm spending, which one would I spend the least amount of money wrapping, and why? If you are thinking the cylinder, because the surface area is smaller, then you are correct. So let me ask you this. What operation would I need to do to go from 0.03, so 3 cents per every 1 square inch, to find out how much money it is for 9,400 square inches? I would need to multiply. And because I multiply, I get that the rectangular box is going to cost me $282. Whereas the cylindrical box is only going to cost me $263. So, like our prediction suggested, we were in fact correct that the wrapping paper for the cylinder is indeed less. Example 3 and 4 do require you to have a calculator, but I'll do my best to explain at least the process without the calculator. So the company you own has a large supply of 8-inch by 15-inch rectangular pieces of tin, and you decide to make them the boxes by cutting a little piece from each corner and folding up the sides. So, for example, if I cut 1 inch from each corner, I go from it being an 8 by 15 to a 6 by 13. And that changes my volume because now I have a 3-dimensional shape. The amount of money I get depends on how much the box holds. So you want to make the box with the largest possible volume. How large of a square should you cut from each corner? All right, so we are again finding volume of this rectangular prism. So we've got base area times height, where our base area is going to be length times width because it is a rectangle. So our volume becomes length times width times height. Now, to find the equation that we're going to need to use to solve for the largest volume, we need to talk about what our new length, what our new width, and whatever our height is for our box. So if I cut out 2 squares of length x from each side, then my new length, instead of it being the original 15, becomes 15 minus 2x. My 8 becomes 8 minus 2x, and my height becomes x. To find the maximum, we'd have to plug it into our calculators, and it would tell us by graphing where the largest x value is that we can cut in order to get the maximum volume. So we're looking for the maximum of our graph. And if you do plug it in and you calculate it by clicking second trace and doing the maximum measurements, you get a maximum at 1.66, meaning that if you cut 1.6 inches from either side or all of the sides, you would get a maximum volume of 90 inches cubed. Example 4 is similar to example 3. However, this one asks for 1, the function that we would need to maximize, and 2, the domain of the function. It does not ask us for how much we should cut or the maximum volume. It just says, come up with an equation and tell me the domain. So Here's our equation, 12 minus 2x, 18 minus 2x, and x. And then to find our domain, we would need to set each piece greater than 0 and solve. So 12 minus 2x is bigger than 0 as long as x is smaller than 6. Once x is bigger than 6, for example 7, you would get 12 minus 2 times 7, and that's not bigger than 0. So we just have to have x smaller than 6. For the middle equation, our x would have to be smaller than 9. And for the last one, x just has to be bigger than 0. So when thinking about our domain, we need an x value that's bigger than 0, but smaller than both 6 and 9. In other words, 0, 1, well, 0 doesn't work because 0 is not greater than 0, but 1, 2, 3, 4, 5, right? Those are all valid, but 7 doesn't work. 8 doesn't work. So our best way to write the domain would just be to write 0 to 6. If we were asked to find the maximum, we would graph it, find the maximum, and determine how much to cut in order to get the max volume. In 4.5, we are able to prove theorems about parallelograms and discuss how parallelograms can be used to solve real-life problems. So, a parallelogram is a quadrilateral with both pairs of opposite sides equal. So our first property is that both pairs of opposite sides are congruent, meaning that they have the same slope. So if the slope of one side is 3, the slope of the other side also needs to be 3. Property 2 says that opposite sides are equidistant, meaning that they are the same distance. Property 3 says that opposite angles are congruent. In other words, if one angle is 110, then the angle that's across from it is also 110. Property 4 says that consecutive angles are supplementary. Consecutive meaning angles that are next to one another, so directly next to one another. And supplementary means that they add to 180. Property 5 says diagonals bisect each other. Bisect means they cut into equal parts. And lastly, the diagonals form two congruent triangles. So this is an example of property 1, property 2, property 3, property 4, property 5, and lastly, property 6. The three formulas that really matter for this section are slope, midpoint, and distance. Anytime it gives you a problem, as like the problem on the bottom of this slide, where you're given 4 points, you should probably plot the points first so that you know what you're dealing with. From here, we can kind of see that it probably is going to be a parallelogram, so we know what we're aiming for. We need to show that both sides have the same slope. That means that AB has the same slope as CD, and BC has the same slope as AD. So I'm going to calculate the slope for both of them and show that they are indeed the same. In property 2, if ED is 12.6, then FC is also 12.6. If RS is 23, then SP is also 23. If ST is 2x plus 15 and RU is x plus 15, we know that they're supposed to be equal, and so we can solve that equation and we can realize that x would have to be 0 in order for that to be a true statement. In property 2, that was dealing with the opposite sides being equidistant, so we need to show that the distance of our sides are in fact the same, and if they're not, then it's not a parallelogram. Step 1 would be to plot the points so that we know what sides we're dealing with. So we need to show that KL has the same distance as JM and that JK has the same distance as LM. So JK has a distance of square root of 26. LM has a distance of square root of 37. And you can kind of tell from the picture that they clearly don't look like they would be equal lengths. Thus, this is not a parallelogram. Property 3 is my favorite. If the angle STQ is 135, then SRQ is also 135. If FGD is 5x minus 9 and FED is 3x plus 11, we know they're supposed to be equal, so we can solve for x, and thus you would be able to tell me that FGD would have an angle measure of 41 degrees, whereas FED would have an angle of also 41 degrees. Property 4 said that adjacent or consecutive angles were supplementary, which means they add to 180. So 70 plus the question mark gives us 180, meaning that our question mark is 110 degrees. On the right-hand side, 80 plus 11x minus 10 would give me 180. Thus, solving for x, I could get 70 plus 11x equals 180. Thus, 11x equals 110, and x equals 10. So you would be able to show me that that angle of y does in fact equal 110. If RT is 19.8, then so is TP because they're the same. So I would have 19.8 plus 19.8 to get me the total distance from R to P being 39.6. The right-hand side is the same type of problem but presented in the opposite way. If the entire diagonal is 23.4, but I only want to know the distance for half of the diagonal, I would simply need to divide it by 2 and get 11.7. In the same way, if I were given 4 points, I again need to first plot them and show that their diagonals intersect at the same point. So we need to show that the midpoint of QS is the same as the midpoint of PR. This is not the case for this one, and thus we can say that PQRS is not a parallelogram. Property 6 deals with congruent triangles, so keep in mind what you've learned about parallels. If the bottom left angle is 52, then this top one on the top right also needs to be 52. And also, what do we know that the angles of triangles add up to? They add to 180. So 52 plus 60 plus the one we don't know adds to 180. Thus, we can solve for the one we don't know, giving us an answer of 68 degrees. Again, the right-hand side, we know the bottom left is 62, so that we know the top right is 62, and we can solve for our missing degree. Let's take a look at this parallelogram to solidify our understanding. First, let's look at the distance CD. That must be the same as the distance AB, and thus it must be 10. The distance from D to A must be the same as the distance from B to C, so it must be 22. A to C must be 13 plus 13, giving us an answer of 26. And DB must be 12 plus 12, giving us a distance of 24. CE we said was 13, while DE we said was 12. Now the angles get a little bit trickier. So our angle ABC, we need that entire angle. And we know that consecutive angles, angles that are next to each other, add to 180. So if we know that the angle in the bottom right is 23 plus 47, in other words, it's 70 degrees, then we know that the angle of ABC must be 110. We already said that BCD was 70 degrees, and if we know that, then we know that its opposite angle, BAD, is also 70 degrees. If we know that angle ABC is 110, then we also know that ADC is 110. BCE was given to us at 23. CDE is using our properties of parallelograms, so we know that the 72 in the bottom left has to match that top right, so we get 72. EDA must match the angle that's missing from our bottom left. And we knew our bottom left in total was 110. We subtracted out that 72 difference. So we were able to calculate that that angle was in fact 38. DEA comes from adding up our missing angles and knowing that the triangles add to 180. We also know that DEA is the same as BEC, just as well as CED is the same as AEB, both being 61. Lastly, we've got EAB being 47 and DAE as being the 23. In 4.6, we learned how to verify experimental properties of centers of triangles and how to talk about points of concurrency in real-life problems. Circumcenter is our first point of concurrency, and it's created by perpendicular bisectors. Again, we see that word bisect, which means cut equally in half. So it cuts our sides equally in half. Notice the definition here. The distance from the vertex to that middle point M, which is the circumcenter, is equal. In other words, the distance from A to M is equal to the distance from C to M, which is equal to the distance from B to M. If it's an acute triangle, the circumcenter is located on the inside. If it's a right triangle, it's located on the hypotenuse. And if it's an obtuse triangle, it's located on the outside. Incenter is created by angle bisectors. In other words, it cuts the angle directly in half. So that means that each line from the side to the middle point M is equal distance. So XM is the same distance as YM, which is the same distance as ZM. Incenter is always inside. Centroid is made by medians. It's the intersection of the vertices connected to the midpoint on the opposite side. So it's going to take a line from A and connect it to the middle point of the line BC. Centroids have a 2-to-1 ratio. So the distance from A to M is 2/3 of the entire distance A to Y. Just like from M to Y is 1/3 the distance of the entire thing. The same is true from BM in comparison to BZ, as well as CM in comparison to CX. Centroid is always inside. You can think of that as being center, being inside. So incenter and centroid always are inside. Orthocenter is our last point of concurrency, and those are created by altitudes. So an altitude, by definition of this orthocenter, we're taking a line from the vertex to the opposite side in such a way that when it intersects with that opposite side, it's perpendicular. So AY is perpendicular to the side CB. CX is perpendicular to AB, and BZ is perpendicular to AC. If it's an acute triangle, it's on the inside. If it's a right triangle, it's on the vertex of the right angle. And if it's an obtuse triangle, it's on the outside.